Thank you, Alan. I wasn't nervous all day until about 10 minutes ago, so hopefully I get the same response. You can take out your phones, sing along with my presentation. It's okay. We've got 45 minutes and they come back. Just kidding. It's a 15-minute presentation. So the title of my talk, it's Moving Energy, Challenges in Transmission and Distribution. In the little write-up, I did say moving energy through space and time. It sounds great. Unfortunately, I'm an engineer, so my talk is very practical about what we do at the center. So where do I belong in the university? Electrical engineering, first of all. But I belong in some part to all these cool labs across Howard College and Westville campus. There's the Smart Grid Lab, there's the High Voltage Labs, there's Materials Science Lab, which I do a bit of work with, and there's a Vibration Lab. So what do we do? And I've got a little disclaimer there. This is my engineer's thinking. We do early research with conferences. We do applied research, which is more journals. We do technology development, prototypes. We have patents. And we'll see a few of those cool things later. We do technology testing. And eventually we get to commercializing products. I really belong to technology testing. That's my real strength. But of course, everything mixes, and out of that technology testing, it goes back and forth. You get journals, you get early research, you go back to prototypes, you find a new angle for a patent or whatever. So what do I mean, moving energy? I mean the movement of electrical energy from the generator to the customer. So generation, thermal, we hear about renewables now, and we've got customers that need the energy. The demand changes over time, and I'll share a little bit of that later. So we're going to move energy over time. And we need to meet that demand over 24 hours. Transmission and distribution, we need to physically move that energy from one place to another. And we do that from 11,000 volts to 765,000 volts in this country, and 550,000 volts DC, which is slightly different. The goal here in moving energy is to minimize energy losses, to minimize impact on the surroundings, and maximize reliability. So transmission lines, this is a 765 kV transmission line. This is actually a Korean test center, and there's some of our colleagues below the tower. You can see how big it is, how difficult it is to get up there and check everything. There's conductors there, they carry current. We need the right conductors to carry current, not get hot, to maximize efficiency and minimize cost as well. We've got insulators that keep those conductors away from Earth, not focusing too much today on that. So the challenge, again, moving energy from your Mpumalangas, which have the massive thermal generators, the massive coal plants, all the way to KZN or the Cape. You've got really long transmission lines, and they've got limitations. They are limited by the amount of current you can put through, how hot they can get. You're limited about the energy loss you get in them, and you want to kind of maximize that. We also want to keep these functioning for 20, 30, 40, 50 years. You only want to do this once. You don't want to keep putting up a new line every few years. One of the newer challenges there is that PV, photovoltaic energy, it's kind of in the wrong place for our systems. It's in the right place for maximum sunlight, but in the wrong place for our transmission lines. And we can do stuff with that, and we are doing stuff with helping solve that. So I'm going to take you through a few of the projects that we've done over the years that have helped contribute to this moving the energy reliably over a long time. The first one I mentioned, overhead lines. They're meant to be there for a long time and reliable. So we need to get up there. We need to see what's up there. And one of the things they do is they fly a helicopter, and they sometimes, they get really close with cameras, or you could put somebody on the line to have a look. you might have to turn off the line. But a few years ago, a very clever student thought, let's put a robot on the line. And there he is, the little robot on the line. It started as an MSc in 2009. Again, this is kind of pointing to that applied research, followed by a patent, followed by more products. So there's the first robot. You can see it in the top there. It's not complete. That's not on a live line. It was followed by a patent technology development project. So the funding changed and they got more money to take it to the next level. Again, there's a close-up of a line. It led to spin-off applied research. We got really specific master students looking at specific problems that they solved. It was particularly interesting because it was difficult to find publications about this, because I think people that develop these products don't tend to publish. And then there was a final prototype delivered to Tokyo Electric Power Company in 2023. So that's selling a robot to the Japanese, which is amazing. And there's a lineup of the four prototypes that were developed. And the next stage for this product is the commercialization stage. So this product, it's owned somewhat by Eskom and UKZN, but it is at the stage where they can roll it out, sell it across the world, which is great. And of course, that'll lead to more research as well. A quick little oh, it's not working. All right. All right. The other projects that we're working on, I thought I'd combine two of them because they kind of talk to the same thing. We talk about conductor efficiency. We need to transmit that energy over long distances. We need to minimize the energy loss. So the power, the energy lost in a transmission line, you can see a little transmission line there. I've got a little red circle there. I've got the sun out. The power loss is a combination of resistive energy loss and the heat from the sun. And what keeps the conductor cool is convection and radiation. So the wind blows, it blows away the heat, and then it just radiates like infrared energy that gets rid of that heat as well. If the power losses are too high, not only do we have high energy losses, but the conductor could melt. And there's an example of a conductor that we've actually melted. We got it hot enough to melt. Whoops. So there's some new technology that's great. It comes with some other issues that we'll see, but it's great. If we get high temperature conductors, we can lower the resistive loss. That's cool. We can apply a special coating to the line, a coating to the aluminium conductor, and that can radiate more of that heat. Right, so the first one, high temperature conductors. Right, so what we've actually got around a transmission line, and you can see it there by the little blue glow, is a really intense electric field. And that electric field leads to corona. It's this little electrical discharge around the conductor. It creates a horrible buzzing sound. So in South Africa, we've got certain limits, and that's why you never see any buildings under these transmission lines. It's that noise. We've got to comply with certain limits. So the equation here is shown. If it exceeds that electric field, we get this noise. So high temperature conductors, they're great, but they do heat up the air immediately surrounding the conductor. So that equation has to change. We found in the lab at Westville that you lower your inception gradient by quite a high percentage when you heat up your conductor. What does this mean? It means that now we can give this equation off to your Escoms, your eThekwini's, hopefully your EPRIs and your international agents, and they can change the way that they design the line so that they can minimize the audible noise, that horrible buzzing. And that's very cool. That's a real contribution that we've achieved. Of course, it needs a lot more work, but we're just about there. So the other big project that we've been involved with for a number of years is these nice guys from Acid Cool in the UK. They're chemists and physicists, and they developed a coating for a transmission line. Now that coating, it radiates that heat away from the conductor. So much so that their claim was 20% improvement in the performance of the line. So that's cool. Right. So what did they need us? They needed us to field test as engineers. So we got great labs and facilities at UKZN. They wanted to see if it performs and sticks to the line under extreme conditions. Right. So the videos aren't showing, but it was quite cool. I had like lots of little arcs going onto the conductor. But essentially, all we did was we ran it at high voltage. We really hit it with lots of corona and arcing, made sure it stuck to the line, and basically we proved that it did work. We have set up an outdoor line. Those that are at Westfield campus might have driven past us a few times. So this line, it's got a weather station. It's got 200 to 300 amps continuously going through the conductor. It's monitored 24/7, 365 days a year from 2019. It's almost been running the entire time. That's great. That's very cool. It gives them great results. It gives me something great to talk about here. The last challenge with that, and this is kind of what the center is about and what maybe the university is about, it's a space where projects can come together, even if we're not kind of the originators of those projects, or they've gone off or moved off into different space. So that line coating, that's cool. Not our product, but we can help them. So their next challenge was getting this coating onto the line. You can't just put it onto a new line. You can't just restring your lines. You've got to do it on the lines that are existing. So we've got to get up there some way. Now maybe we knew a company that came from the university that developed robots. And there it is. It's a good space where two companies that were separate at the beginning have come together to develop a new product. And there it is, recently being tested in Scotland. The last challenge is, so those were long, old projects that are kind of finalized now. The next project I want to talk about is maybe a future project that's gaining a lot of traction. So Dr. Nyati spoke this morning about a little bit about generation, demand, etc. So demand, it's what the customer wants. What we want, we need our energy in our homes. And you can see it's got this odd shape. So in the middle of the night, obviously we're not using energies, we're not running our washing machines, we're not doing our dishwashers, we don't have the kettle on. So there's very low demand. In the evenings, when we come home from work, we've got the oven on, the kettle on, the TV on, the radio on, the pool pump on because we forgot to put it on in the morning, and we've got this very high load. So that demand fluctuates. It's not that easy to deal with. So our base generation, it's thermal and nuclear in this country, and you can actually see how much it is. It's a really high percentage of generation. What I also want to point out is it's really kind of flat compared to the demand. So it is flat because you need to run those generators at a certain point to keep their efficiency up. They don't change just suddenly like the load does during the day. So we've got to do other things to kind of keep it running like that. On top of that, I've now added all our new kind of generation, our PV, our CSP, our wind generation. And you can see that that is not constant during the day. I'm going to point out particularly to the PV. It's the yellow. You can see it's only there really in the middle of the day. That's not where we want it. It really isn't. Right, and just on top of that, if they do generate excess energy, such as excess PV during the day or wind, and we've already met the demand, that energy just gets lost. So the dotted line there, again, that's the PV. So we need to move that energy in time. And we've got a plan. Right. So we know PV, it's a fast technology. It's the fastest to go up. We can move that energy. We've got pumped storage. We've got that in this country. It can charge or can pump into your hydro plant during the day when the PV is high, and then it can discharge at night when the PV's when there's the requirement for it. We've got new battery storage, but they have their limitations. I'm not going to go too much into it because you can see it there. What I am going to point out, though, is the pump storage, 2 kilowatt hours per meters cubed. And it's also a slow technology. It takes years to get a dam built. It takes years to get this technology done. So we've got a colleague here who's come up with a plan for liquid air energy storage. It's not geographically constrained. It's bulk storage. It really is just those big tanks that you see outside a hospital storing liquid nitrogen. Same concept. Energy density of 200 kilowatt hour per meter cubed. It's an expandable technology. You can leverage other things like waste heat, cryogenics for other aspects. So it's a really viable technology. This is our new big project. It's in the technology development stage with the prototype in the pipeline. We already have a patent for this, and we're looking for electronic, computer engineers, mechanical engineers, mathematicians, computer scientists, physicists, material scientists. So we're busy getting this off the ground, but again, I come back to this is kind of that technology development place, but we still need the applied research. So we've got students working on techno-economic feasibilities, optimizing usage of the storage, grid flexibility, leveraging waste heat and cryogenics. Right, so kind of the point of the talk was that there are a lot of meaningful projects out there that can contribute here, and everything is at different levels. I'm particularly good at one aspect, but there are lots of other people that are good at other aspects. Everything blends. So what I didn't quite demonstrate, maybe a little bit, is that when you're running multiple projects, they kind of all blend into one, or not blend into one, but maybe aspects of each of those projects can contribute to the other project. I think also the theme for today, and I'd already written this, so it's not new, but collaborating with others. And the space is great. If you get talking to others, you might have the next big idea, such as a robot for the line. There are people here that would be interested to take that forward. You need patience as well. Those big projects, they take time. That robot project started in 2009. It only really completed 2023. So you've got to have patience if you want to be here that long. And lastly, there is help. This conference is great. This symposium is great. Because it gets you out there, it gets you talking to other colleagues who may advise you how to get that help, whether it's financially, where to look for a certain type of project. And I kind of feel that it is getting better. Prof. Kubanali mentioned the NRF is changing the way they do stuff, and kind of there is that help there, and it's coming and it's getting better. Cool, thank you.